So we start with a correction. Yesterday, I said something very quickly, and on the train ride yesterday, I had a panic attack because I thought that's just silly. So we gave a definition for log of z, which is not a function, right? It's a multi-valued function, and if z is written in polar form as r e to the I theta, then log of z is the natural logarithm of r plus I theta, where we call theta is any one of these angles given by the argument of z plus all multiples of 2 pi. Fine, which means that if we want to write our log z as u of r theta plus v of r theta I, and then check to see if this function is analytic, right? Then we have this criterion that says you need to check that u and v are continuous, that all the partials, well, I should use r here and theta, all the partials are continuous, and that Cauchy-Riemann in polar form equations hold. So if all these things hold, then this implies that log z is analytic, right, on whatever domain we're talking. And I said clearly ln of r is continuous, theta is continuous, the partials, right, which were 1 over r and 1, those are continuous. We checked the Cauchy-Riemann equations and they held. Therefore, except at 0, where this isn't defined because you can't have ln of 0, we're happy, right? So this thing is analytic everywhere. Any problems with that? There should be. What's the problem? Well, the problem is actually in the most idiotic, stupid place. Okay, ln of r, there's no problem here. This is a continuous function. Theta, well, when we go down to, well, I mean, this isn't so much of a problem for log z, except for the fact that you can't talk about log z being analytic. It's a multifunction. But if we go to L, capital L, where we now replace our theta here, right, with the one where it's just k is 0. So if we replace it with just the argument of z, we know that the argument of z always lives between minus pi and pi, right? That was our convention. And so what happens if we graph things? Well, if I choose a z over here, the argument for z, what's the argument for z here? Well,
it's almost pi.
Yeah, something almost pi. Now, what if I just go a little bit on the other side? Okay, so here's, for instance, z bar. Okay, what's the angle? Well, the angle's actually almost negative. Almost negative. And I can get really, really, really close to the edge here, and another point really, really close to the edge, so that the 2 points themselves are really, really close together, but their arguments are wildly different. Right? It goes from positive all the way to negative. That's not the way continuous functions work. Continuous functions have the property that if you make the inputs really, really close together, then the outputs are really, really close together. So in fact, this thing is not continuous on this line here. Right? Now, it's okay away from the line. If you're off this line above, it's fine, because then you can always ensure that, well, there's a little There's a little ball around your point. And continuity is a very local property, right? You move very, very close. And if you put a ball around it, then good, fine. You have continuity in here. But on this line over here, the negative real axis, all those points, right, if they go up a little bit, I mean the angle here, the argument for these points is pi on the button. If they go up, it's a little less than pi. If they go down, boom, they're negative, way, way away from pi. So that means that this log function, when we're not writing down the log z, is continuous, except on the negative real axis and 0. We already knew it wasn't continuous at 0 because it's not even defined at 0. But the negative real axis, it's not continuous anywhere on there. Again, why? Because of the argument property. If you change the argument, if you change this step, move it up a little bit, the argument doesn't hurt. It doesn't get hurt. But if you move it down, the argument jumps wildly to negative. If it's not continuous, it's certainly not analytic. So, in fact, the log function is not analytic except at 0. It's analytic except on this negative real axis. Sometimes it's called the principal branch cut. Or just the principal branch. So the principal branch is everything but this negative real axis. So that's just it's an important point we left out yesterday. The derivative, of course, where it is defined, is still 1 over z. Everything we did after that was fine. But you have to make this allowance that you... So before, when you're talking about real functions, you couldn't have a logarithm of anything non-negative. And we still have that problem. That, well, we can have a logarithm, it's just not continuous. When we said you know what log of -1 is, we computed that. Right? But it's not continuous at -1. Okay, so that's a correction. Now we want to get to complex powers. Not to be confused with rigid power. Sorry. Should have warned you before I used you this material. Alright, so the question is, if z and alpha are complex numbers, what is z to the alpha? And the long-term answer to this question that doesn't give you the real answer is, or the imaginary one, is that unless alpha is an integer, then this isn't a function. It's not even a function. I mean, normally, z squared, that's a good function. Z to the alpha will not normally be a function. It will again be a multi-valued function, just like the logarithm is, with lowercase l. So how we want to define this? Well, we already have this log sitting around, so we might as well try to use that. We know that the log is the inverse function for e to the z. So that means that, right, z, or rather e, to the log of z is supposed to be z.
Can we use logs just like we do in the real world, where we take log of z, the alpha, and the alpha
D. Z to the alpha is e to the log of z, the alpha. And of course you can just multiply this. We don't even need this formula that log of z to the alpha is alpha log of z. Which, by the way, is that true? Well, we actually answered it yesterday, but it's also on your homework, so I'll let you.
Wait, what? What was the question?
Is that property you just said true? That log of z to the alpha is alpha log of z.
E to the alpha.
So we, well, like I said, we did that yesterday actually. We didn't write it down that way, but we actually answered that question yesterday. And it's on the homework, so you'll get a chance to go back and answer that question. So I'm asking, does this basic property from logarithms hold, right? That if you do log of x to the n, this equals n log of x. Does that hold for complex values? So that's on the homework. Okay, so here we have a perfectly reasonable way of writing down z to alpha. It's e to the alpha times log of z. And we know what log of z is. That's the point. Right? That's already been defined. And notice this is lowercase log. So we can write this further, right? We know what log of z is. Log of z is ln of r, where here r is, again, we'll say polar form. Z is already, did I say that? So it's ln of r plus I theta. And remember, theta is the argument of z plus 2 pi k. So here k is allowed to run through all integers. So what is immediately obvious from this is that, well, as k runs through all the integers, you get different exponents. And so in general, you should get different values. And so since there's an infinite number of these k's, you should be able to get an infinite number of values. So in general, when you take a complex number to a complex power, you get an infinite number of answers, just like with the logarithm. Okay, so that's in general. So generally, z to the alpha has infinitely many values. I like that abbreviation. Infinitely. So what I want to do is show you when this thing is only going to have one value. Let's give you a specific case where it does. When it might have more than one value but only a finite number, and then when it's going to have infinitely many. All right. Now, I'm not going to give you all possible ways of getting those three different sets, but this will be useful anyway. So the first case is, what if alpha is already just an integer? So this should be pretty straightforward. If we use this definition, then let's see. So our z to the alpha, let's rewrite it here, z to the alpha is e to the alpha ln of r plus I times the argument of z plus 2 pi k. Okay. Okay, so let's see here. Well, the first thing is, what's the argument of z going to be? Well, we don't know, right? What's alpha going to be? Well, alpha is just some integer. So let's multiply it through and break this up into two bits. I'll multiply the alpha all the way through. this first bit is just some real number. Now the second bit, let's see, let me break it up further. Second bit I get e to the I alpha arg of z. And then the last bit I get e to the 2 pi k alpha I. Now what is e? Well, if there was no k or alpha there, I'd have e to the 2 pi I. What is e to the 2 pi I? It's 1, right? Because it's sitting over there at 2 pi, which is, and it's on the unit circle, so it's 1. If I put the k there, remember k is an integer. Does it change the value? No, right? It's just, it's 4 pi or 8 pi or negative 12 pi or something. They're all sitting there 1. If I put alpha in, remember that alpha in this case is still an integer.
It's still 1.
It's still 1. So this goes away. So this is just e to the alpha ln of r. And now I put these back up as one. I'll put this back up as one thing. Arg I times the arg of z. Of course, you like this is again. This is just log of z with big L. This is e to the alpha big L log of z. Which has just one value, right? Remember, log of z is an honest to goodness function. So if you take a complex number and raise it to an integer power, you actually get a function. Z to the alpha is a function in that case. So let's say I want to take 1 plus I and raise it to the 40th power. What should this be? Well, I guess we have lots of... Oh, I miss it. That's on the last one. Okay. Let's put it in this form here, maybe. Okay, so first you have the e to the alpha ln of r. So the alpha is 40. And the ln of r, well, we need the r here, so what's my modulus for 1 plus I? Square root of 2, right? It's 1 squared plus 1 squared, which is square rooted times square root of 2. And then you have to raise it to the, or to multiply here by 40, right? So e to the alpha is 40, and then you have ln of root 2, and then a plus, right? Or we could do it separately, e to the I, and then we need the argument of z. So what's the argument of 1 plus I?
5 over 4.
5 over 4. I, 5 over 4. Now, what's really nice here,
Times 40.
maybe another way to write this, let's actually go back above for a second. If you write this as e to the ln of r to the alpha, just the first bit, e to the ln of r is just r, because they're inverse functions. So actually you could write this first bit here as just r to the alpha. And then you'd have times e to the I arg of z. So actually we can simplify this. Okay, we just said r was root 2, and alpha is 40. So root 2 to the 40 times e to the I pi over 4.
Times 40. 40 I.
Oh yeah, times 40. Right? We need the alpha up there too. Okay, so times 40. So okay, root 2 to the 40th. That's 2 to the 20th. And e to the I pi over 4 times 40. Well, it's 40 pi over 4 implies that's 10 pi I. Now e to the 10 pi I, that's, well, it's just over here again, right? That's 5 times 2 pi I. So what is this? This is just e to the 10 pi I, which is a multiple of 2 pi I. It's just 1 again, right? This whole thing is just 1. Okay, because it's 10 pi I. 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. Okay, so this is actually just 2 to the 20th power. So 2 to the 20th is actually a 40th root of 1 plus I. Or vice versa, rather. 1 plus I is a 40th root of 2 to the 20th. Who knew? Okay. So the second case is going to be if we replace integer with rational number. So that means alpha looks like m over n, where m and n are integers and n is not 0. Okay. So, of course, the definition is still the same. We still have that z to the alpha is e to the alpha times ln of r plus I times the argument of z plus 2 pi k. Before we broke it up and used that k was an integer, or that the alpha was an integer to kill all the 2 pi k alpha I bit. We're not going to be able to do that here because alpha isn't an integer. But, well, it's almost an integer, it's a rational number. So we should be able to sort it out a little bit. So everything we did, we can do again, exactly the same way. And we'll get to right here. And the only difference is that we're not going to be able to say this is equal to 1. So let's just copy that. Z to the alpha, right, ln of r, which, well, that's actually r to the alpha. And then you have e to the I argument of z times alpha. And then you have e to the 2 pi k alpha I. As long as I have alpha up there, let me replace alpha with m over n. That's what alpha is. Now in principle, these k's can run over all integers. But this should actually look somewhat similar. As k runs through over all integers, so does k times m. No? Is that true? Maybe not. Let's see. Let's say k was, let's say m was 2. Let's see, that would be 4 pi k. Well, I guess you're not getting anything less. What if m was 3? Then you get 6 pi. And then, well, maybe you're kind of missing out, possibly, things. We'd have to think, right? Have to check. What is true, though, is, okay, when we divide by n, you remember what happened before when we tried to come up with nth roots? Is you would look at, okay, you'd have your principal root, and then you'd add 2 pi over n. And then you'd add another 2 pi over n, another 2 pi over n, another 2 pi over n. You keep doing that. And eventually, you'd end up, after n times, adding 2 pi again. Right? Well, the same thing is happening here. As soon as k becomes an n, this becomes a multiple of 2 pi again. It really becomes n, right? Right? K is n, then you get a multiple of 2 pi. If k is 2n, then you get another multiple of 2 pi. If it's 3n, you get another multiple. So it's just going to cycle and repeat, right? As soon as k gets to n. So just like when you're looking for nth roots, the only things that are going to give you something different or when k runs between 0 and n minus 1. As soon as it gets to n, you just cycle back to the same value again. Okay, so this is what's happening in the rational case. This m, notice here, doesn't really matter a whole lot as far as how many roots. It doesn't matter at all. Right? The number of roots you get is dependent on the n. You should probably reduce this rational number. So we might as well assume they're relatively private. So that means greatest common divisor. This notation, m comma n with parentheses around it, is GCD. Okay, so let's do another example. Let's do 1 plus I to the 3/2 power. Okay, so now we're raising it to a rational number. So we'll see. Again, you need the r, but we know the r. That's root 2. And now it's raised to alpha, which is the 3/2 power. And then we need e to the I times the argument. Well, we still know the argument is pi over 4 times alpha. So we have pi over 4 times 3/2, and then we're going to add all these. So you have 2 pi k, again, times 3/2. Pull the I out. So let's see here. Root 2 to the 3/2. You get 3 pi over 8. Okay, so here k is running between what? 0 and n. N here is just 2. So it's actually just 0 and 1. So you have e to the 3i times 3 pi over 8 plus 2. 2's cancel. 3 pi k. And k runs from 0 to 1.
Can't you just say 2 to the 3 over 4?
Where are we talking? Here? Yeah, this is not so. This is not the important part of the problem, right?
Yeah, that's neat.
As you like. Okay, so there are two solutions here. K is 0, k is 1. When k is 0, you get root 2 to the 3/2, e, well, is to the 3 pi I over 8. And if k equals 1, then you get root 2 to the 3/2, e to the, well, let's see. When you add 3 pi k, well, k is 1, so you add 3 pi, that's just taking, okay, adding 2 pi would send you here, adding 3 pi is back to pi. So it's like basically multiplied by minus 1. It's just going to stick a minus out here. And you're back to 3 pi I over 8. So this minus comes from the 3 pi. E to the 3 pi I is minus 1. Okay, so there are two roots here. Or the two solutions. Right. So the last case is where you have a complex but not rational number. And, well, that's where you're going to have, in general, an infinite number of solutions. I don't really need to. There won't be a derivation here. It's a complex number but not a rational. And we get our formula. R to the alpha, e to the I, R to, well, I'm forgetting alpha. An alpha plus okay. So now the thing is this: when alpha is a complex number, which is not rational, then in general you're never going to get repetition. Right? Here we are very lucky because after n values of k going in, you killed this n here and you went back to 2 pi and you just started the cycle over. In general, right, k is just an integer. You're not going to be able to multiply it by one of these complex numbers and end up getting another integer. You can't do this. If you multiply by an integer to a complex number and you end up getting an integer, then you must have started with an integer or a rational number. Okay, so in general they're just infinitely many answers. So let's do a couple examples. How about 1 plus I to the, I think I want to use 1 plus I. No, just to the I. Okay, faster. So 1 plus I to the ith power. Okay, so let's see. So we need r, which is, again, root 2, raised to the alpha. Alpha is I. So we need root 2 to the I. But I don't want to actually use this form. I want to do something a little different. I want to go back to this form for a second. It's, when we work it out, you'll see why. I think it'll be a little bit easier. So let's go with this form. E to the I times ln of r, so that's root 2, plus I times the argument of z. So what's the argument of z? That was again pi over 4. Plus 2 pi k. Now let's see, I'm going to multiply this I through everything. Maybe the other form would have been correct. Let me multiply the I through everything. And I get e to the I ln of root 2. And then look at this, this I turns that I into a minus I, or minus 1. So it just becomes minus pi over 4 minus 2 pi k. Right? Or if you like, minus pi over 4 plus 2 pi k. And this second part, which is in all the other examples, this second part was the imaginary part, but now it actually becomes the real part. So this is e to the negative pi over 4 plus 2 pi k. Okay, this is now your r. This is the norm of the vector in polar form, times e to the ln of root 2I. This is in polar form. It doesn't look like it, but this is your r in polar form, and this is your theta. So the r, and this is a real number here. Well, it's several real numbers. As k runs through different values of z, this runs. Now you might think, well, wait a second. When this k runs through all values of z, this is just multiples of 2 pi. Doesn't that just give you the same thing? And why not? Because it's not our theta, right? There's no I up here. If you put in different values of k, these just give you completely different values of r. Right? There's no I to say, oh, we're on a unit circle. These are just real numbers. So this gives you an infinite number of moduli, it's the length, and then this is the angle.
So it's a line.
Yeah. As it sits on the same angle, but the radius changes. So that's kind of cool. And let me work another example for you. Let me just throw a little piece of terminology at you. The log function, as we saw, that there's a special one, right? The capital L log, and if we use that, then we might call it the principal value of the logarithm. For all these z to the alphas, well, we might want the principal value of that too, and we do it in exactly the same way. It's just where k is 0. Right? So the principal value is just coming from this, right, which is actually coming from if you use capital log in your formula. Another nice example, it should be easier in fact, but I love it because of the answer. So I was in high school when I first tried to figure out what this was. And I spent a good amount of time trying to do it before our pre-calculus teacher, Mr. Sewell, showed us. But now we can do it quite easily. But I just think it's pretty neat. You can figure out something like I to the ith power, which sounds so bizarre and strange. Okay, so what is it? Well, you take, where's our formula? E to the alpha is I, times the natural log of the radius, or the norm rather, that's 1, plus I times the argument of I. What's the argument of I? I is up here.
Pi over 2.
Pi over 2. So I don't need that. It's the argument, so pi over 2. Plus 2 pi k. Now this ln of 1, that's just 0. So that goes away, and then this I multiplies in and gives you a minus 1 there. So it just becomes e to the minus pi over 2, right, plus 2 pi k. K here runs through the integers. So the principal value of I to the I is e to the minus pi over 2. Now, why in the world should it be the case that you take a complex number, something simple like I, raise it to a complex value, and out pops a real number? Not only that, but, well, if you don't look at the principal value, but you look at every value, there's no i's up here. Every single value of I to the I is real. Okay? This is a tad peculiar, you think? And then, not only is it real, but it comes out to be e to the minus pi over 2, which is, one, quite short, and two, and it's using a lot of these symbols, these constants. I mean, if you ever wondered why e and pi are so important, how they show up like this, this is really quite baffling. So everything just works so perfectly like that. So the I is also the ith root of e to the minus pi over 2. It's corollary of this. What does it mean, the ith root? Well, how do you do the second root of something? How do I write that? Like, if I want to write the second root of 2, I can write this. Sorry, some markers. But how do I write this without funny symbols? 2 to the 1/2. So if I want to write the ith root of something, what should I write? 2 to the 1 over I. Of course, Christina is over there ready to say that that's just the same as
2 to the negative I.
negative I. Okay, so you can use either one. It doesn't matter, right? From this point of view, you can do as you like. But so now you can say, what's the ith root of something? It's kind of strange. What is this? You can check it. E to the, okay, we need alpha. Alpha, say, is minus I. Times the natural log of, well, the radius of 2 is just 2. ln of 2. Plus I times the argument. Now the argument of 2 is just 0. Plus 2 pi k. Let's see here. This is going to become your imaginary part, and this polar part sort of, and this is going to become the real part. So minus I times I is actually 1. So this is just e to the 2 pi k times e to the minus ln of 2 times I. So the principal value, when k is 0, this just becomes a 1. And so the ith root, or the ith root of 2, e to the negative ln of 2I. So it's, in the end, it's not so hard to do these things. It just takes a little work to build up the definitions to do so. Okay, so on the homework, there should be a lot of practice for you. I think that's a good place to stop for the day. Let me remind you, tomorrow we won't do a new material lecture. We'll be giving you an opportunity to ask questions. So remember, try to be prepared. So I'll accept homework questions, but also if you have conceptual questions, that's always good. And then next Tuesday we'll start the really hard stuff, which means this weekend you have some extra homework, which is to read ahead the section on contours and line integrals, because you need every advantage you can get. I mean, the course is going to pick up. Business is about to pick up. So, any questions? You guys are quiet today.